So we're going to continue. In the last class, we had some just come here. With some idea of a brief sort of conceptual and historical development of how quantum mechanics has started. So in this class, we'll just say that the way we had this idea of wave particle duality, which was in light, when we imposed that understanding for matter waves. So it was a bit difficult to imagine. So that's why a psi as a wave function, which will describe the state of the system, it has in it the idea of particle and waves are somewhat embedded as a concept. And in some limited experiments, we also found that if we have a pin, the way we had Young's double slit experiment, that we have a set of electrons or particles which will pass through these things. So at the end, you can also reproduce a diffraction pattern. The way we produced a diffraction pattern in the case of light photon. But the thing is, the more puzzling part of it is that if we just close one of this thing, that still we are able to observe diffraction pattern. So the moment we try to decrease this thing, we want to just decrease the size of that pinhole, the diffraction pattern gradually ceases to be there. So in a sense, that was shown by a property of complementarity. The more we try to focus on the particle aspects, the wave nature becomes fuzzy or less descriptive and vice versa. Now, in today's thing is how we can see wave packets, free particle motion, and wave equation. So it's like, so if you have a particle, if you have particles, matter waves, which have the properties, attributes of, for example, where the wave spread is maximum, we say its particle is supposed to exist there. So if we assume that a given particle is not a particle, it's series of waves, they are superposing, and then they are superposing. The way we took the analogy of stationary waves, they will superpose in a certain amount, and the energy exchange is also given by certain discrete levels within these matter wave particles, whatever you might call it. Matter wave, waves which sometimes have as if we are studying particles. Got my point? For example, electron is not an electron. Electron is itself made of small waves. They are superposing, and after superposition, where the amplitude is maximum after superposition, we say the electron is supposed to be there. This is our understanding. Now, this correspondence between we're just basically trying to make a base. We cannot go directly to Schrodinger. Before Schrodinger equation deals with psi, we can write it like this. It's a partial difference equation. Psi ka evolution in space-time. One is time-dependent Schrodinger equation on this. But the thing is, first we should know what is psi. Because psi is not like the classical particle, Newtonian particle, point particle. In point particle, you simply you apply a force, the particle moves from A to B. But here it's not the particle, it is psi. So the description of psi is somewhat different from that of a particle. So iska jo evolution, the evolution of the psi will be how you have to study evolution of psi. So since we have said that psi is not a particle, so it's got evolution, which is given by this Schrodinger equation. So before we have to understand psi, then we can understand its evolution. So we are trying to have a background of psi. how we can describe psi in terms of wave packets. Then once we just have it, we'll just study the Schrodinger equation. Got my point? Otherwise, you will not be able to differentiate between. So, वहाँ पर there was a particle. It has also an evolution. But now here it's a psi. Psi is not a particle. So first we should have a description of psi. How it spreads. What's the wave spread? So once we have that thing, then we can go for the time independent Schrodinger equation or time dependent Schrodinger equation. That's it. Comes after that. हाँ, exactly. So we'll come to that. So now there is something called principle of super. So before coming to principle of superposition, we say that the correspondence between quantum to classical motion serves as a guide to construction, serves as a guide for construction by the superposition of harmonic waves, by the superposition of have you ये आपने थोड़ा सा harmonic waves पढ़ी है, Fourier waves. So असली ये है कि you can have all sorts of waves, whichever wave you are thinking harmonic. So because the waves don't come in exact amplitude, cos omega plus sin omega t. So there should be a general wave in which you have the superpositions of all sorts of waves with all sorts of amplitudes, with all sorts of descriptions, frequencies. So उसी को एक general prescription है that was given by Fourier analysis. How we studied general superpositions of all waves. With all frequencies, all amplitudes. For example, this simple sine wave, कोई wave ऐसी होगी, कोई ऐसी होगी, है ना? There can be. So how they will superpose in nature? So basically, we are also trying to study matter waves, basically at this thing. So they are not even classical waves. So they are matter waves having wave and particle properties in that sense. तो अब ये है कि इसका जो harmonics है, how we are going to see. So what is the guide for the saying that we say that the superposition of harmonic waves of wave packets that propagate like classical particles but exhibit quantum mechanical spreading in space and time. So you got what he wants to say. To superposition of harmonic waves. So we'll have an analogy of these waves of having different frequencies, which are propagating and then they are superposing. Now what is the difference? So, but they are wave packets. They are not particles. So once we enter into quantum thing, they are not particles. They are wave packets. Where the wave packets, while they are superposing, where the amplitude is maximum, we say the particle is there. That's there. It's not like a particle. So it is superposition of wave packets. They propagate like light. They don't propagate. We use the word they propagate light. So that is weird. They are not up. So we'll take an analogy. They propagate like classical particles, but exhibit quantum mechanical spreading. Quantum mechanical spreading in space-time. So where the spread is maximum, we say as if it's a particle. Where the spreading thins out, we say it's sort of wave. So this is how we try to have a gross or macroscopic, or we can say rough understanding of how we can visualize wave particle, this thing, how we can visualize matter waves in that sense. And it becomes pronounced once, for example, if k is the propagation vector lambda, so the de Broglie wavelength can be written as p is h k. So if you want to write k is what? Propagation. 2 pi is what? It's like 2 pi is like this. It's number of frequencies or wavelengths which are traversed in a given wavelength. You know? That is known as propagation. So if you want to write propagation in terms of de Broglie wavelength, this is momentum. So you can also write it as h is this is h by 2 pi. This is mv. This is k is 2 pi by lambda. So you can write it lambda is equal to h over mv. It's basically we are trying to just say how we can write, हम कैसे लिख सकते हैं wavelength को in terms of these things. And now अब हमारे पास what we have, the thing is in our case is, for example, we have so we have for example we have a wave function psi x, y, z and t. This is wave function psi. It's psi 1 and psi 2 is x, y, z and t. These are two wave functions. So if it's, we have to see how they will superpose. How they will. So if an electron or if a proton or if any quantum mechanical particle having a wave function psi 1, another particle having a wave function. So where the subscripts x, y, z, these are the space, in space components, evolution space. It's evolution time. This is evolution space. So if these two will superpose, so normally, so the total wave function psi 1, psi x, y, z, t will be psi 1 plus psi 2. Now the point is that so you can have an analogy of this superposition principle. So now in since previously we also said that wave function psi जो है इसको हम we represent it by what? Psi square as an amplitude of as the intensity, the way we have intensity of a light, उसका square आता है. So in the same way, this, since it's a psi and psi star and its complex conjugate, that will come out to me. So we have represented this wave function in terms of complex conjugate. Complex conjugate. So the square of the complex conjugate, that will give us the intensity of the wave function psi square. So that analogy is helpful. So here how we just जो हमारे पास जो screen था ना, ये two where it's bright spot, again bright spot, then maxima, minima, maxima, minima. How we calculate when you study any book on optics? How we calculate the fringe width or maximum intensity and minimum intensity? That's I square by 4 as a filter. So in the same way, you can, that analogy comes helpful if you try to imagine the psi in terms of wave function. So psi square. So, but what is the difference is that the amplitude of psi 1, so this is the intensity of this thing. This is the intensity of, but once we say psi 1 plus psi 2, so it's not this psi 1 plus psi 2 square. It is basically, it's basically what? It's psi 1 plus psi 2. So it's not that you are going to write the intensity of psi 1 square plus psi 2 square. Because these two waves will interfere. They are going to superpose. It's the superposition of these superposed waves, uska intensity, rather than, so that square of psi 1 square is not equal to psi 1 square plus, because there will be factors of ऐसे आ गए, it will come out to be psi 1 square plus psi 2 square plus psi 1 psi 2 star plus psi 2 star psi 1. So these will be two additional factors once we open them inside that set. Because इसका अगर conjugate भी है, उसका conjugate squares, it will come back, it will come. So it's not, you should not confuse this. So if with the intensity, if we are going to superpose two, it's not necessarily two waves. You can have psi 1 plus psi 2 plus psi 3. So as many wave functions as much possible you are going to have. So but if we see अब ये है कि फॉर एग्जाम्पल वंस वी स्टडी सुपरपोजिशन ऑफ वेव्स, जो ऑप्टिक्स में हमारा जो है ना हाइगन्स प्रिंसिपल हम करते हैं, द फॉरवर्ड वेव एंड द बैकवर्ड वेव, देयर वी टेक समटाइम्स एन अप्रोक्सीमेशन दैट बैकवर्ड वेव विल नॉट एक्ट ऑन द फॉरवर्ड वेव, सो अप्रोक्सीमेशन हम लेते हैं, दैट्स इट. अब ये है कि इट्स नॉट नेसेसरली, इट शुड नेसेसरली वर्क, दैट अप्रोक्सीमेशन शुड आल्सो वर्क फॉर द matter waves also. So this is another point. Now अब हमारे पास क्या है, in a sort of a description, if we want to write psi in terms of cos wave or in terms of sine wave, ऐसे हम लिखेंगे. Before coming to psi being represented as, because जो हमारे पास ये है iota kx या kx है, ये है ना cos of kx plus sine of. So it's also sort of whether a wave is like this or it's like it's sine wave or cos wave. It can be superposition of sine with sine. So any wave can be represented as, if it's a complex wave, it's for iota kx, it will be cos x plus iota sine x. Cos x is cos wave, iota is the imaginary part, is the sine wave. Now you have to see the superposition of, if you have psi 1 plus psi 2, you have cos x1 plus cos x2 plus iota sine of x1 plus sine of x2. It's like that. If you want to superpose two complex waves diagrammatically, but in principle, if you want to imagine, it becomes more complicated. It's the simplest. Pictorially, हम कैसे represent करेंगे in a simplest sense. So अगर हमारे पास, for example, ये है, सो जनरल फॉर्म है psi 1 जो है हमारे पास, psi 1 is equal to this cos of kx minus omega t plus delta sine kx minus omega t. So a plane wave, so you can represent any psi 1, for example, in terms of this cos function as in terms of sine. This a delta here used as a constant. Can take it as an amplitude or joule. So a plane wave moving in negative x direction can be written as, so in the x direction अगर can be written as, so अगर x direction हो तो कैसे होगा? This k will propagation, यहाँ just, it will not be k, it will be minus. Forward direction हो गया k, minus will be, so in the next direction, negative direction, it will be cos of minus kx minus omega t plus delta times sine of, this will be minus kx minus omega t. So again, the way हम जो analogy लेते हैं, normally कौन सी वाली analogy लेते हैं? We are taking the analogy of stationary waves. Yes, a wave comes here and the wave comes back. So if it's confined between certain regions, this wave, so it will have यहाँ पर maximum, यहाँ minimum होगा, minimum superposition, यहाँ maximum होगा. So that analogy also is here. So if you have a sort of superpositions of two waves here, that analogy is, that's why we sometimes get the discrete values, because in quantum mechanics हमारा जो exchange interaction है, it's some discrete amounts, so it's a sort of analogy. So So y and z can be omitted because we are just concentrating with the x plane only. Yes, yes. Or you can say that cos of kx minus omega t plus epsilon. Epsilon is some phase which can be 0 or whatever, it depends. Or this is delta is sine of kx minus omega t plus epsilon. So now here it's Rukai. This is what it looks like. But इसमें थोड़ा सा you have to do work at your place. इसको आप in terms of homework you try to cos a, sin b, sin a, cos b. फिर terms the same terms on the left hand side you can write it as a of epsilon is cos of kx minus omega t plus delta times sine of kx minus omega t. Now if you compare the coefficients, this with this with this, so you can say cos of epsilon plus delta sine of epsilon is a, and delta cos of epsilon minus sine of epsilon is epsilon a delta. So it's a bit of work. You have to see, you have to compare this equation and this equation. Then comparing the quotient of this with this with this. So you can have this in this. So what if we say the argument of the book is that if you just have this way of writing it, this can be better represented if we write delta square को हम in terms of minus 1 लिखेंगे या delta is equal to plus minus iota. Here delta if you just so this equation can be better solved if delta has a value, this imaginary value, this has an. So the whole point to mention is that we will have to represent this thing in terms of complex value, psi in terms of complex value. So psi in terms of complex value, how does it come into picture? We can represent it psi as this and this. So इनका जो superposition है उसका ये आएगा, and it's better helpful if we just have this thing analogy here. This we'll take 2 seconds. Okay, we'll just take 2 seconds. Okay, we'll stop here, and in the next class we are going to start how we can properly represent this psi in terms of wave function. But the only thing is that you have to verify this at your place, this and this. Okay.